so this will be a short discussion on section 4.3. We will discuss the notion of complements and conditional probability. The chapter also covers something called Bayes' theorem, but we do not cover that this semester. There should be no homework questions assigned from Bayes' theorem. If there are, I sincerely apologize. All right, so complements and conditional probability. We met complements back in 4.1. I'm going to go over the definition again. And now we're actually going to use them in a very, very, very useful way. And this truly is how the notion of complement, one way it gets used for real in the land of statistics. So complements, you'll remember the notation A and A bar. And I like this because some addition rule problems can be recast as multiplication rule problems. I will remind people that A bar is every event not in A. Between the two of them, A and A bar cover the entire sample space or gamut of possibilities. And as I say, there are some addition rule problems that can be recast as multiplication rule problems. And this turns out to be exceedingly useful, and it makes a cumbersome problem much more easily manipulated and calculated. Now, we are going to be looking at problems that talk about the probability of at least one occurrence of some particular event. That is to mean one or more outcomes is observed for a particular suite of observations. It's also important to realize that we will be working with the complement of at least one. And it's important to realize that the complement of at least one is none. At least one or more. The complement of at least one, none. Let me give you an example of what we mean here. We're going to flip a coin twice. We're going to assume it's there. The event I am interested in is the outcome of at least one head. Now, I will note in my sample space for the two coin flip, head, 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 tail, tail, head, tail, tail. The outcomes with at least one head are these right here. The outcome with no heads at all is the complement. So I will note that the complementary event means none, no heads at all. That means the first selection came up with a tails. The second flip also came up with tails. Now, I will remind you about the relationship we developed for complementary events in our first section. The probability of an event A is equal to 1 minus the probability of the event of the complement, A bar. Coins do not remember, and the probability that I have a tail on my first flip and a tail on my second flip is literally 1/2 times 1/2. 1 minus 1/2 times 1/2 is 1 minus 1/4, or 3/4. So the probability of at least one head is 3 out of 4. Now, I picked this example because I note that I can calculate this with the classic method. The probability calculated using our classical method is also 3/4. There's 1, 2, 3 out of a total of 4. So we get the same result. This is really designed to convince you that maybe switching to a multiplication is a little bit more straightforward than working with the initial example. Why is that? Let me explain. That means the probability of one head or two heads or three heads equals David had a question at the beginning that was somewhat similar to this, where we were making a number of selections. So this means I've got to worry about lots of double counts. I'm not going to bore you with how tedious that could become because it really doesn't push the discussion forward at all. But it should help you think that maybe this might work to switch from a multiplication, in addition to a multiplication. This is much easier to work with. So let me go ahead and note in a slightly different ink fashion here that the probability of at least one occurrence is equal to 1 minus the probability of no occurrences at all. This is where we use that multiplication rule. It's quite effective. So let me give you an example of this. So, and by the way, this is why we want the rule, and we don't want to rely on trying to draw our sample space and count things up. It gets super tedious. So we're going to flip a coin 10 times. Probability, we're going to look for the probability of an event A. The probability of at least one heads. So the first thing I want to do is to recast that in terms of the complementary event. A bar means that we have literally no heads coming up in our 10 flips at all, none. That means that the first flip is a tail, and the second flip, and the third, and fourth, and fifth, and sixth, and seventh, and the eighth, and the ninth, and the 10th flip are all heads. These are independent events. I can multiply those probabilities together directly, and there's 10 of them. So the way it looks when I recast this in our formula is the probability of A, at least one head, is equal to 1 minus the probability of no heads. That's equal to literally, and by the way, when I do this problem, I do not put all these steps in. This is really designed to help us why we need the formulas that we do use. So I have 1 minus the probability of a head on the first, second, third, all the way out to, we have them out here, we have them 10 times. So that's 1 minus 1/2 times 1/2 times 1/2, 10 times. That is literally 1 minus 1/2 raised to the 10th. So we see the result there. Let me jump over to my calculator and we'll go through the keystrokes. So I have 1 minus. Now, here's the thing, people. There are times when the order of operations matters. There are times when it doesn't. So I now have 1 minus the fraction of 1/2 raised to the 3/10. You notice I have the 1/2 in parentheses. Those of you who remember your algebra will note that the formula tells us we have to apply that power of 10 to the numerator and the denominator. There's my probability. Most of you will type in, and then you'll pick up the caret key and raise this to the 10th. And you'll end up with the right answer, and you'll have no idea of why you're going to get other questions wrong. Let me point something out. If my fraction was something other than 1/2, there will be a really big difference in these two expressions. You see the difference in the two expressions? And it's because without the parentheses, the 10 only applied to the denominator, the number it was directly next to. You didn't have an error up here because what you calculated was 1 minus 1 raised to the 10th divided by 2 raised to the 10th. And 1 times 1 times 1, even 10 times in a row, is still 1. So people get away with a bit of an error there. Sometimes it bites you, sometimes it doesn't. Those of you that remember the order of operations and the importance of parentheses will be well served for problems such as these. So I multiply that together, and there we have it. 0.9999023, 3 significant digits. The first non-zero digit, I take a look at the fourth to tell me what to do with the third. So we have a 0.999. And there we go. So that brings me to the end of the first part of section 4.3. You know, I have 8 minutes. I think I'll go ahead and try to finish this, even if I go a little bit over. If you guys need to bail, that's fine, but I will finish this and it will be posted on our website by tomorrow. I really like this next topic, this notion of conditional probability. I like it because it rewards the student who understands what is actually being asked. It's not overly complicated, but if you can parse or separate out what is actually being asked, these questions are probably the easiest of the entire semester. If you have trouble with that, on the other hand, they can be the most confusing. So we have what we call conditional probabilities. Conditional probabilities. Let me tell you what a conditional probability is. That's when something will happen only if something else has happened. That's a conditional probability. I asked this gal out in high school, and she said, yeah, sure, when hell freezes over. That's a conditional probability. If hell ever freezes over, I got myself a date. But until that happens, I'll be crying alone. Now, that's too much information, I realize, but that's all right. It's important to realize, however, that this conditional probability is calculated after a first outcome is known. I cannot overemphasize this fact. It's calculated after a first outcome is known. We even have special notation for that. We introduced it in 4.2 when discussing the multiplication rule. We have the probability of B given A has occurred. That straight vertical bar is the notation that means that A has occurred. The bus has left the station. And I'm going to remind you of the actual equation that we utilize to calculate probabilities for multiplication. The probability of A and B occurring is the probability of A times the probability of B, given that A has already occurred. It's a simple equation. I can solve it for the probability of B given A by dividing both sides by the probability of A. A little bit of rearrangement gives me this formula here. I will use the formula in a moment. I think I'll use it once this semester. I prefer to use my intuitive understanding of the question to actually solve conditional probability questions for a course such as this. What do I say there? I almost never use the formula. Here is the intuitive approach, and I am going to use it first, and then I will use the formula. Ideally, this will convince you to think about these problems rather than just, freak out and run away. And here is the important component. The intuitive approach, we're going to assume A has occurred. I know, assume, make an ass out of you and me and all of that. But we're going to assume that A has occurred. This really, really, really helps. It enables me to ignore almost all of the data in those complicated tables. And I use that calculation. Well, this is important to limit what it is we must do numerically. Now, let me show you how this works. I have some data here, male and female data, on whether they voted or did not vote. You'll notice I've already gone ahead and calculated row totals and column totals in my grand total. You're going to need some of these values. The other thing is the language here. We're going to find the probability of selecting someone who voted given that they are a woman. Now, our book is fairly consistent with this, and I am 100% consistent with this when I write the problems into our quizzes and our exams. And the given means that event A has indeed happened. What is my event A? The event that we have selected a woman. Now, we're interested in if that person has done what? Voted. So take a look at my notation here. We've got the probability of selecting someone who has voted given they are a woman. So I told you that the condition allows us to ignore much of the data in the table. Here it is. Because we're selecting a woman, the only data I care about is right here in this row. This is the only data that matters for this problem. So, how many women are there? There's 102. How many of them voted? 79. We have 79 over 102. And Mr. Calculator tells me that 79 divided by 102 is equal to 0.7745 and change. 0.775. So 3 significant digits. Once again, The 5 tells me what to do with a 4. That's why it's a 5. So that's the intuitive approach. The given tells you where, what row, or perhaps what column to focus on. You ignore everything else. I'm a math teacher, and I will look at the formula. So by our formula, the probability of selecting someone who voted, given that they are a woman, that's the probability of selecting someone who voted and is a woman. Remember, there's really just a single selection here because the first one has already happened. For that first probability, selecting someone who voted and is a woman, those are the votes out of 246. So the probability of selecting someone who voted and is a woman in a single selection is 79 out of 246. That's what you see right here in my numerator. What's the probability of selecting a woman? There are 102 women out of 246 individuals. So the probability of selecting a woman is 102 out of 246. Fraction divided by fraction, that's a complex fraction if you remember some basic algebra. If you do invert and multiply as you should, you'll find out you've got some cancellation, and look at what I end up with. 79 over 102, which is exactly the same thing I had with my intuitive approach. So with rounding, 0.775. So conditional probability, use the intuitive rule. So given event A, limit it to A. That really is the secret to doing these conditional probability problems. There's really nothing else to them. The formula, honestly, it's a little gift from the devil of math. The intuition helps us a lot. So I'm pretty much done. Are there questions? I will get this. Oh, yeah, let me stop my recording.